Okay, so this is our last section, chapter 2. It's about linear approximations and new idea. So we talked about this idea in the past, but let's just refresh it. What does it mean for a function to be different? Okay. So I can take a derivative. When you say the limit exists, is there a specific limit you're talking about? So I'm going to say function must be continuous. If the function is continuous, does that mean it's differentiable? No. So differentiable is something else. So back to this idea of a limit. What limit is it that must exist? So let's say, so for a function f to be differentiable at a point A, is it enough to say this is true? Is that the limit we're talking about? So just as x approaches A, the function has a limit? So what limit is it then? Yes, I mean, if we're saying that, so if we're saying a function is differentiable, then basically what you're saying is the derivative exists there. And if the derivative exists there, that means this limit that we've talked about. This limit that defines the derivative. This one must exist. Now, that other function, that other limit that I just erased, this has to be true because, as somebody said, the function has to be continuous. If you're going to talk about a function being differentiable, it must at least be continuous. Anything else that we can say about what a function, what it means for a function to be differentiable? I'm not sure if I heard it or, but this is also true. So the derivative, I mean, really, this is just another way to restate something we've already written. Derivative exists at x equals A. So because we've been doing a lot of derivatives lately, most of the functions, not all, but most of the functions we've dealt with in the last month or so have been differentiable, at least the points we care about, but really most of them have been differentiable everywhere. Are there any functions we've talked about that are not differentiable everywhere? There's at least one, and maybe you don't remember it, but absolute value is the one I was thinking of. So let me show you a little bit of illustration here. So if I open up this graph in Desmos, so a couple things I have graphed here. So the curve, the red, is the function y, or f of x equals 1 over radical x. The blue line is the tangent line at that green point. So the green point is x equals 1/4, y equals 2, and then I graph the tangent line at that point. So this function is clearly differentiable at that point, right? What do you think is going to happen if I zoom in to A? What are you going to see with the way the tangent line and the way the curve react to each other? Just touches the one point. But if I zoom in a little bit, so knowing that we have a continuous differentiable function, and I'll tell you that 1 over radical x is differentiable everywhere is defined, except for, actually everywhere is defined. So what do you think might happen if I zoom into this point? They're going to start to look the same, right? So didn't mean to do that, but if you zoom out, obviously there's nothing alike, right? They have one common point, and at that point, they have the same slope, but really everywhere else, they have nothing in common. But if I start to zoom in around that point, we can see that they start to resemble each other, right? And the reason that's true is because, we know that limit exists as you get very, very, very close to that point A. But when we take that derivative, the limit really only, we're just looking at that one point. We found a derivative of 4, but the slope of that curve is only -4 at that one place. So really what I'm doing when I'm zooming in here, I'm just making my values of X that I'm looking at a lot closer to that point. So right now, my X-axis goes between 0.235 and 0.27. And it looks like the curve has disappeared, right? So before I show you a counterexample, does it kind of make sense why the line and curve look like they become the same thing as I zoom really far in? All right, so as a counterexample, what was the non-differentiable function that we talked about? Absolute value of X. Okay. And I need to zoom. So that tangent line doesn't make any sense anymore. But one thing I will tell you is this. That point doesn't make sense anymore. So we talked about the absolute value function before. It's differentiable everywhere except for one place. Where is that one place? 0, right? So here's what I want to do. I want to, let's just say y equals 0.1x. Because, and the reason I'm saying that is because, based on what we've said a tangent line is, like the really bad, clumsy definition of tangent line, that is a tangent line, right? It touches that function at one place. But I can't really call it a tangent line because this derivative isn't really defined. What's happening as I zoom in here? Nothing. So kind of a graphical representation of why that function is not differentiable at that point. Something else we talked about when a limit exists. If a limit exists, it can have one value, right? Can it have more than one value? So one thing we've talked about with limits, and kind of goes back to one-sided limits. For a limit to exist, the one-sided limits have to agree, which means if there's a limit that exists, it can only be one thing. It's going to be unique. And I think you'll agree that I can just make, I could pick any slope out here that I want, and I can make what we think of as a tangent line where it's just going to touch in one place, right? But because I can't make a unique one, that means that that's kind of a graphical representation of why that derivative doesn't exist. So more talk about the idea of differentiality or differentiability. Any questions on any of that so far? The big idea we want to use today is that, if you have a function that's differentiable, then really in that little small neighborhood around that point, what you're looking at is you're going to kind of be able to approximate that curve as a straight line. So let's look at an example of that. So we're going to look at this function here. Already projected. So I want to linearize this function. F of x equals the square root of x plus 3. And if I'm going to come up with some tangent line, if I'm going to linearize, I have to, center it at a particular place. So that particular place in this case would be a equals 1. So I want to use that to approximate this derivative. So can I find a derivative of this function x equals 3, or sorry, x equals 3, square root of x plus 3? Okay, what is that derivative going to be? Times 1, right? So yeah, I mean, we've got an application of chain rule there, power rule. If I do one little rewrite, I'll get 1/2 times x squared to x plus 3. So are we okay with that being the derivative? So we're going to come back to this, but I want to look at another diagram. But for now, let's just keep a pin in this derivative that we found. So basically what we're doing is this. This is the function that I just talked about in the dark black. This is f of x equals radical x plus 3. And we got these two different but related variables for changes in y. So one thing I'll write down here first is this dy dx equals f prime of x, which is something we already found, but for now we'll just leave it general. So based on this diagram here, do we understand what the differences are between the deltas and the d's? How am I using them differently? Like what does delta x, what do delta x and delta y represent? Change, so I mean, and in the x direction, I'm calling them the same thing, right? So what's the difference between delta y and dy? Right, so one is the change that comes from the function itself, right? So let's represent that delta y like this. Really, delta y is going to be equal to, whatever the value of the function is there, minus whatever the function was valued at originally. So delta y has it has to do with the function itself, right? This is based on f of x, not f prime. F of x. But that change dy, look at how the dy is represented there. What's that dy a measurement of? Or how am I measuring it? Am I measuring it from the function or am I measuring it from something else? It's based on the tangent line, right? So one thing I want to highlight here is this dy dx relationship. So up until now, we've just talked about dy dx and f prime of x. We kind of use them interchangeably because they mean, they're both ways to write the derivative. But what if we split the dy and dx apart and we have something like this? Dy is equal to this thing that we'll unpack in a second. So would you agree that dy still stands for a change in y? It's not the same change that delta y talks about, but it's change in y, right? Okay, so let's talk about it. Basically, it's the product of these two things, f prime of x and dx. What does f prime of x tell you? That's the derivative, right? And what's the derivative mean? Slope of the tangent line, right? Or in this case, it's the slope of this blue line, and it's also the slope of this black curve at that point. They're the same. So this right here is a instantaneous rate of change. So that's an instantaneous rate of change. What does dx represent? Some change in x, right? I'll say a small change in x. So clearly the delta y and the dy are different. And that comes from the fact that, for one of those, I'm using that straight line to get that change. The other one I'm using the function. And because those two things are different everywhere except for one place exactly, they're going to be different. But what do you think's going to happen as we zoom in and get really, really close? Like let's say we try to make delta x or dx really, really small. What can we say about dy then? Yeah, we're going to make it small as well. So this idea of linearization really only makes sense if we're somewhat close. And I'm going to go backwards to get back to the example we cared about. So we want to use this linearization to approximate these two things, square root of 3.98 and square root of 4.05. Are these pretty close to that a value of 1? So let's go ahead and keep going now. So we wrote this idea down before, dy dx is equal to f prime of x. And from there we derive this, dy is equal to f prime of x dx. So really what we're doing here is something we've done a lot of. If I'm trying to linearize a function in some neighborhood of a point, really what I'm doing is I'm giving the equation of a tangent line, which is something we've done quite a lot of. So can I find the equation of the tangent line to this function at this point that I care about? What would that slope be? More importantly, how would I find it? Comes from the derivative, but what value of x do I need for this derivative? Not 3.98, and here's why. So the linearization I'm about to do for this function, I'm asking for it at a very specific place. I'm going to use that line to approximate the square root of 3.98 and square root of 4.05. But the actual approximation itself is going to be based on this x value of 1. This is where I want to find the tangent line. That should come out to 1 over 2 times the square root of 4. So 1/4. And that value of 1 comes from basically, if you're going to linearize around some point on a curve, you have to pick a location. This is a very local, it's in the definition. By local, I'm saying it's only going to be valid around some chosen point. All right, now if we find the rest of this equation, y equals mx plus b. We know that m is a fourth. We know that x is 1. What's the y value associated with x equals 1? 2 square root of 4 plus b. So from here, I should get the b equals 2 minus a fourth, so 7/4. How big of the y equals 2?
X equals square root of x.
Yep. So yeah, y equals f of 1 equals square root of 1 plus 3. I'm not saying these are equal, but I'm saying that as long as I want to restrict myself to x values that are pretty close to 1, this is true. Square root of x plus 3 is approximately equal to 1/4 x plus 7/4. So now I want to find this. I want to find approximately what the square root of 3.98 is. So if we're going to apply, or we're going to use our linearization to figure out or to approximate the radical 3.98, I need to figure out the x value that goes with that. What x value do I need to choose to approximate this? 0.98. So 0.98 plus 3, which means this is going to be approximately equal to 1/4 times 0.98 plus 7/4. I got 1.995. What is the actual square root of 3.98? 1.99499. So as long as I stay close to it, would be my y values are going to stay close as well. We can do the same thing with radical 4.05. What x value I care about this time? 1.05. So not equal to, but approximately 1/4 times 1.05 plus 7/4. What's that equal to? $2.0125. And just to show one thing in the margin here, what if I use this thing to approximate like the square root of 25? Right. So if I use my my linearization, I'll have 1/4 of 22, which is 5.5 plus 1 3/4. So that'll be 6.75. Obviously, nowhere close to what the actual square root of 25 is. So for these linearizations to work, you I can basically, these are the approximations of the square root of those two numbers that come from this tangent line. So let's go back to my this thing here. So if we fit this picture to the example we just did, what are the coordinates of this point here? No, the actual point P. Right. So this is the only place. So I mean, it's approximation, which means it's going to be you're allowing some error in the situation, but there is no error when you're exactly like when you're at that 0.12 because they have the same slope there and they have the same location. So the two examples we looked at were this. We looked at this one here and this one here. This was x equals 1.05. And this one here is x equals 0.98. Now, the process we just went through to get the square roots associated with those, did we get those values from the blue or the black? The way we did it, we used the line, right? We used the equation of the tangent line we came up with. So we're going to be a little bit wrong. But if we stay near that point P, we can keep our errors small. As opposed to, what was the one that I did? Yeah, so x equals 22. So I mean, it's not meant to be globally accurate or faithful. Go ahead. Yeah. Yeah. This really there really isn't much new we're doing here. We're trading some of our accuracy for simplicity. I mean, if I basically what this gets used for, I'll give you a real world application. A lot of computer programs that, deal in approximations would rather run like this. You'd rather run them like this than to calculate some complicated, through some complicated function, because the computing time is going to be much different, especially if you're doing it thousands or millions of times. All right. Another thing we're going to look at is this. Basically, you can use this idea to kind of predict what. Here's what I could be wrong. The instruments I'm using are only accurate to 0.05 centimeters. So if I can measure length to that accuracy, I'm trying to figure out, given that tolerance, given that possible error, what might that do for, which is the volume. So I can measure the radius of the sphere. I'm trying to figure out how that affects the volume of the sphere. So what's something I should write down that relates those two? Yeah, so I know how those two things are directly related. And basically what I'm looking for is, usually when we think of a rate of change, we think of things actually changing. Like for everything up to now, we've kind of assumed that, we can perfectly analyze how long a radius is, what the volume is with these rates of change. Now we're seeing what happens if we can't be quite so certain of that. So this error really is a rate of change. So the rate of change that I'm introducing here is this: dr equals plus or minus 0.05. This is true of a lot of things. If you try to read that clock up there, it's accurate to the second. So you can't really tell beyond that, nor do you really care. Maybe you don't really care about the error, but sometimes if it's something you really want to be accurate on, sometimes it will matter. So I have this idea of dr, and this thing right here is called a differential. We're so used to looking at these changes as happening together. So a rate of change of y would. Right. So I'm really looking for dv. So I have dr, I want dv. What should I do to this volume equation we wrote down? Let's use it to find dv dr. What does dv dr mean? Right, so that's the rate of change or the differential of the volume with respect to radius. And these are things you know how to do. And I think we even did this exact one last week. dv dr equals 4 pi r squared. And let's do something we haven't really done in the past. Let's rewrite this like this, knowing that I can talk about these changes separately. So I want to find the maximum error of the volume of the sphere. So really, I'm looking for, want to find the maximum of, and I'm going to write it like this, the absolute value of dv. So I really want to look at if I have underestimates too. So what's one value I should plug in for DR here? Or first of all, what should I plug in for R? 21. That's the radius I measured. And then the DR is basically going to be by how far I take them off. So based on this, oh, I missed something just now. Where that? So let's use this to calculate how wrong my volume might be. I'm going to round to whole numbers because of how big they are. 277 centimeters. So is that the maximum error, or should we look at something else? Question, Zach? Right. We really should look at both ends. Or we can write something down and see if we need to go any further. 21 centimeters squared times negative 0.05 centimeters. Take a look at that. Is there a reason I need to do that one too? That was going to be the exact opposite. So I can say the maximum error here is going to be 277 cubic centimeters. It could be an underestimate, could be an overestimate. Under or overestimate. Any questions there? Go ahead. Yeah, we very well could. Well, really, I mean, we found that the error, so we wanted the maximum possible error. The maximum possible error is 277 centimeters cubed. It could be an error on either side. Thomas? Right. That's why I put absolute value in dV. And just to kind of give a more context here, typically what you might do is this. Let's assume we're right. What is the volume of this sphere? I got 38,000. So, and this is pretty common in engineering settings. With your instruments, or if you have some inaccuracy, which you always will. So, all right, the volume of the sphere is 38,792 cubic centimeters with a tolerance of 277 cubic centimeters. Sebastian? Anything else? All right, so I got one side of a right triangle, which is known to be 20 centimeters long, and the opposite angle is measured as 30. So let's draw a picture. And I want to measure this thing. What's the percentage error? So I have my 20 centimeters, which I know for sure somehow. I have my 30 degrees, which I've measured. which might be wrong by a degree on either side. And I want to somehow use that measurement to figure out how long that hypotenuse is. So what's an equation I can use to bring all these things together? I don't think Pythagorean theorem will get us there because we know one side, we want another, and we know nothing about the other, the third one. I heard a vote for sine. So we could use law of sines, but do I have to get that complicated? What are law of sines and law of cosines really helpful for? Finding angles and what kinds of triangles? Yeah, not right triangles. Have you ever heard the word oblique triangles? Yeah. So yes, law of sines will work there. It's a little more high tech than we need. So let's just go with sine. So what's the sine of 30 degrees? Not like the actual ratio, but in this case, yeah, 20 over x in this case, right? And really, I shouldn't be calling that 30 because it's called theta. It's going to have variability. So the sine of theta is equal to 20 over x. So what is the differential I know something about? Maybe we should back up. What are the differentials that are going to come from this situation? Is 20 going to be variable? Is it going to have some kind of error to it? No. Somehow we know that for certain. We don't care about this bottom side at all. Is theta going to have some variability in it? Yeah, we have some error there. So let's kind of catalog those things we have. We have d theta, which is the error in measuring. Angle. And I'm going to underline the word measure, which hopefully will become clear in a bit. The other differential is dx, which is the error in not measuring, but calculating length. Do we understand why there's a difference? Why am I saying measuring in one place and calculating in the other? For whatever reason, I'm not really looking to measure that hypotenuse. I'm trying to calculate it based on other things I can control. All right, so which one of those two things do I have? D theta or dx? D theta. So how can I relate these two things to each other? Or how can I get d theta and dx involved here? By bringing these things together as dx d theta, what kind of operation does this signify to you? Right, so rate of change, derivative. And I'll give you a choice here. Should we solve this thing for x, or should we just differentiate it the way it is right now? You could. So let's do that. Oh, no, that's not what I mean. So x is not really 40, right? We think x is 40, but we also have some error baked into the way we're doing this. What I mean by solve for x, I can just do this. X equals 20 divided by sine theta. What is 1 over sine theta? So now if I want to take a derivative of this, dx d theta, what is the derivative of cosecant theta? Yeah. I'm glad someone said something because I was only like 80% sure that was it. That's a good question, though. I'll answer that by saying this. Do you know what the derivative of sine is? Do you know what the derivative of cosine is? Do you know the quotient rule?
Yeah.
That you can get all the rest of them. Because I wanted the derivative of cosecant theta, right? Let's say I have no idea what that is. I can't remember it. What you do know is that that's going to be the same as this. 1 over sine theta, which is kind of the long way around, but you can apply the quotient rule to that and get to the same place we wound up. Thomas? You can. No. Well, there might be a test like that, but so the way the mastery test works for this class is, so it's basically just like, you just take derivatives of a bunch of functions. The goal is 90%. If you get a 90% or greater, you get 100% of the test. If you get less than 90%, you get 90% of whatever you got. It's kind of a weird testing instrument, but it's reality. It exists. Jordan?
How does 1 over sine theta quotient?
I mean, it's
Your denominator function as you just do sine and negative.
Yeah, you can also do sine theta to the negative 1 and treat it like a table. Yeah, I mean, so I guess I'm going to say my answer more confidently. Or anything besides sine and cosine. I mean, the sine and cosine you probably should have committed to memory, and you probably already do. And the good news is you can get the others from those two. All right, where were we? Okay, so we got our derivative. I'm going to rewrite this like this. Dx is equal to negative 20 cosecant theta cotangent theta. All right. Oh, I forgot d theta. So I'm trying to find dx, right? What do I know about d theta? Yeah, so d theta plus or minus 1. So let's, man, I am totally out of room here. Hopefully you're okay if I buy some of it back right here. And I think unlike the last case, I probably am going to need to do both sides because they're going to be different. So dx is equal to negative 20 cosecant of what angle? What do I think theta is? Yeah, so that's what I measured. It's 30 degrees. Cotangent 30 degrees times d theta. Times d theta, which is plus 1 degree for now. What is the cosecant of 30 degrees? If the sine is a half, then the cosecant is 2, I believe. Tangent 30. Tangent 30 is 1 over radical 3. So cotangent is radical 3. And this is kind of a weird thing. I'm going to multiply these like length measurements by a degree. Doesn't really make a lot of sense. So is there another unit we should be using here? We should probably be talking about radians. So instead of 1 degree, what is 1 degree in radians? Probably seen this thing in the past. I know that pi radians is equal to 180 degrees, right? So 1 degree is going to be pi over 180. And from there, I can get my error in the distance. I believe the possible error is 1.2 centimeters. Do I need to do the estimate on the other side? Is it going to be different? I think it's going to be positive, right? So I think what I've said is this: the absolute value of dx is equal to 1.209 centimeters. So we're almost there, but that's not really what we were asked for. We were really asked for the percent difference, the percentage error. Is that something we remember how to find, or do you need a refresher on that? Okay, so I know my error is 1.209 centimeters, but without the percentage error, I have no idea if that's any good, or if that's close, or maybe I'm trying to measure a thing that's only 1 centimeter long. In this case, I'm trying to measure something that is how long? What's that? 20? Actually, not 20. And I'm going to go back to this idea of a nominal value. The nominal value is basically what happens if, assuming that there are no errors. What are your measurements? Let's say I am dead on that theta is 30 degrees. If theta is 30 degrees, what does that mean for x?
40 centimeters.
Yeah, so x equals 30 degrees, or theta equals 30 degrees, implies that x equals 40 centimeters. So this x equals 40 centimeters, that's my nominal value. So if I want to find my percentage error, to be equal to this. What's my greatest possible error? As a proportion of what I believe that measurement is. And I'll translate that to a percentage. And with our last task here, this is 3.02%. Where did we get 40 centimeters? Yeah, so using this relationship here. So we measured theta to be 30 degrees. Assuming that's certain and accurate, then that means that x would have to be 40 centimeters. Any more questions? Thomas? So this really comes from, and I don't have time to develop it all in more detail, but I can later if you want me to. In radian. And not obvious, but really all that canceled in doing this is the degrees. Pardon?
You said
So measuring I can observe. So in this situation, I have direct control of the thing, right? And for some reason, I don't have to observe this thing. So I
Well, this is a line. And this measurement I can control. I need to calculate.
All right, I think I've kept you later than I need to. Last call for quizzes on your way out. Otherwise, I'll see you Wednesday.